Okay, I want to spend a few lectures looking at the catabolism of, or the breakdown of amino acids. We've started with the deamination, and now after the deamination has been done, we have to kind of think about how else what we're going to do with the rest of the carbon chains. Just removing the amine doesn't really necessarily deal with the full extent of breaking down these amino acids in productive ways for the body. Now, to get into this, I actually want to take a step back from the deamination and look at some PLP reactions. So some general PLP reactions. And what I want to do is abbreviate the PLP cofactor as just an imine on the nitrogen atom of an amino acid. So we've looked at, and this is going to, I think, be a little bit more helpful for you all as you try to digest the various possible reactions that PLP can undergo. Now, what we're going to start with is the transamination reaction. So the transamination deals with the, and sorry, let's draw the deals with this structure. So we have our R group. And now what I've got here is just PLP, adducted by way of an external aldimine to our amino acid. Now for this reaction to, for transamination to work, what we have to recognize is that all PLP is really trying to do, all PLP does, all these figures in the textbook are wonderfully written and wonderfully designed, but PLP is a big molecule provided by biology to make it so that we can stabilize a negative charge at the alpha position of amino acids. So when I see PLP, I recognize that I can support a negative charge at the alpha position either through just a deprotonation. So I'm going to have a base come in and deprotonate. That's going to form a negative charge at this alpha position. Now, what we do in the case of transamination is we take that negative charge and we sort of push it down and push the double bond over to pick up an H+, which gives us an isomerized imine which can react with H2O to form a keto carboxylic acid. If you want to have that O protonated in every case, go for it. Doesn't bother me. Okay, just biological conditions, it's probably not protonated. So we can have transamination. We've looked at that, but what else can we do? We can also do elimination reactions, particularly if we have a hydroxyl group at that beta position. So here's our our amino acid adducted to PLP. And what I want to do is at the beta position, I want to put an OH. So what we can do is we can deprotonate the alpha position. Why do we deprotonate the alpha position? Well, because that alpha position is acidic because our amino acid is adducted to PLP. So I'm going to take the electrons from deprotonating that alpha position and push off the OH as though we have a net loss of water. We lose an H at the alpha position and the OH at the beta position to give us this structure. And you can see how that's a stable structure because we have a lot of conjugation. So this is important particularly with serine and threonine. Okay, so serine and threonine can give us structures like this. We can also, in addition to elimination, we could look back at that beta hydroxy group and do a retroaldol reaction. So we have two beta hydroxy amino acids. Beta hydroxy carbonyls are generally products of an aldol reaction. So why does PLP help us there? Well, what we can do is we can do a retroaldol. Now, a retroaldol works backwards from an aldol reaction. You can think about it this way. The X minus deprotonates the OH. We push electrons here, and we push electrons to the alpha position. Okay, we have some aldehyde. Let's not worry about that right now. Still have our amine bound to PLP. The negative charge at the alpha position is stabilized because the amino acid is bound to PLP. But if we look, that amino acid, or that negative charge is just the structure of an enolate. So this is called a retroaldol reaction because the forward aldol would be addition of an alpha position, addition of an enolate to a carbonyl. So this would be the forward or the typical aldol reaction. So because we're bound to PLP, we can stabilize the negative charge at the alpha position. That's why they call it an electron sink, because you can add more electrons and it just goes down the sink. We could draw a bunch of resonance structures that look glamorous, but the structures, the drawings get a little cumbersome and the structures get a little complicated to remember, especially if you're just learning this stuff and being introduced to it the first time. Okay, so we can form a stabilized intermediate. Instead of going back to the aldol reaction, which isn't productive, we could just go to H plus here, and we get to a PLP glycine adduct. That is at the alpha position of our PLP adduct. We have 2 hydrogens. That looks like PLP glycine. Okay, if we have a carboxylic acid at that alpha position, and we always do, right? We can do a decarboxylation reaction. So the decarboxylation reaction involves taking our alpha amino acid that's bound to PLP, which means we can stabilize negative charge at the alpha position. I can't hammer that home deep enough. If we can stabilize a negative charge at the alpha position, what we can do is decarboxylate that alpha position where we lose CO2, and the CO2 is lost. The CO2 was negative, now it becomes neutral. Where does the negative charge go? It goes at the alpha position where it's stabilized due to the electron sink from the PLP. Okay, if we do a decarboxylation, we can actually add, well, we can push the electrons through, but we can add an H plus either at the alpha position, or we could come down and add it to the position nearby the PLP. If we do the latter, we get a new sort of imine that we could react with water to form an aldehyde. Pretty cool. It's all very cool. And the byproduct there is that pyridoxamine phosphate that we talked about, the first, intermediate in the transamination that in the transamination that we need to then react with alpha ketoglutarate to regenerate our PLP adduct to the enzyme active site. Okay, we can also do a so we talked about decarboxylation, retroaldol. We can even do a retroclaisen reaction. So a claisen reaction is where we take an enolate and we react it with an acid halide equivalent, some carboxylic acid derivative with a good leaving group. Okay, so instead what we're going to do is the retro version of that, where we, Claisen reactions can make ketones. So we're going to break a ketone and make a carboxylic acid derivative. So the common way is to have some sort of S group. We'll put it as S minus, they're pretty acidic. S group attached to the R is going to attack the carbonyl, come back down, and we're going to lose the entire PLP fragment. We're going to lose a glycine fragment through a retroclaisen reaction. Okay, so that's actually going to give us, in this case, a thioester plus our glycine anion, which could do a number of things. It could be protonated at the alpha position, and we could protonate it at the position on the PLP to generate PMP after reaction with water. Number of approaches, but I just want to take a second to reflect on all the things that PLP can do. It can do so many different types of reactions, all of which are interesting and critical for understanding how we break down amino acid side chains. And I feel like this is enough of an informational lecture. Let's go ahead and stop here. We'll pick up with the catabolism in the next lecture.